Hi, welcome to this lesson on calculus, applications of the first derivative. Let's have a look at using the first derivative, question 1. So we're given a function f of x equals 2 times x minus 1 all squared minus 8. So we want to classify any stationary points, intervals where the function increases, and where the function decreases. Alright, so first of all, looking at this function f of x, this is of the form of a completed square of a quadratic function, x minus p squared plus q. Okay, so my a value here is positive 2, so therefore I'm going to have this shape here with a minimum turning point. And then the turning point is also given in that vertex form, so that is going to be when x is 1, then y is negative 8. So we can go ahead and draw a rough sketch of this diagram. So let's go ahead and do that. Okay, so I've got my axes. Alright, and then let's go ahead and put some points on. So we said at x equals 1, which is about here, then the y value is negative 8. So there is the turning point, and we know that this is going to be part way between the intercepts, right? And it's going to have this shape here. And then it turns at that minimum turning point and then increases again. So we can see from this graph already some of the properties, such as the stationary point is most likely going to be at this turning point here, because that's when the gradient, which is the derivative at that point of this tangent line, is probably going to be 0. And then we can see on this interval from the turning points, which is 1, negative 8, that all the values here, the tangents, are increasing in terms of their gradients. And then to the left of 1, all the tangents here are decreasing in their gradients. So it's most likely that the derivative on the right side here will be positive, and the derivative on the left-hand side here will be negative. But we'll go ahead and do that algebraically using our differential calculus techniques. Okay, so first of all, let's find stationary points. So what I'm going to do is with this function f of x, I'm going to expand it out first. So x minus 1 squared, that's going to be x squared, double the product, so minus 2x, plus 1 squared is just 1, minus 8, and then expanding further, I have 2x squared minus 4x plus 2 minus 8 will give you minus 6 in total. Therefore, the first derivative, f prime x, is going to be using the power rule and then the sum and difference laws for derivatives. We'll have 4x minus 4. Okay, so for stationary points, I'm going to set the first derivative equals to 0. So this is equivalent to saying 4x minus 4 equals 0. Okay, take 4 across on both sides, divide 4 on both sides, and we therefore get x equals 1. And that's what we came to expect, because 1 here on the x-axis is that turning point there. Okay, so therefore the stationary point is given by the turning point, 1, negative 8. Okay, what about intervals of increasing? Okay, so the function increases when the first derivative is set to be greater than 0. So again, this is equivalent to 4x minus 4 greater than 0. It's a linear inequality, so we can solve it algebraically. Take the 4 across, we have 4x greater than 4. Then dividing both sides by 4 gives us x greater than 1, where x is a real number. So that's the inequality notation, but I much prefer the more rigorous notation, which is your interval notation. So how would we write that? It'll be, or you could say x is element of, not including 1, because of that strictly greater than, all the way to positive infinity. Okay. Then where's your function decreasing? Well, it's decreasing whenever the first derivative is set to be less than 0. So again, we have a polynomial inequality now that we can solve algebraically. So if we follow the same steps, we'll get x less than 1, where x is a real number. Okay, and then in interval notation, that would be x is an element from negative infinity all the way to positive 1, but not including it. Okay, so that is the solution to this type of question, and we can see it very nicely graphically if we are able to sketch the function as well. Awesome. I'll see you in the next one.